so this is a line. Okay, so I will check your attendance. Lecture 17. Okay. 이재혁 씨, 오하늘 씨,
네.
심준호 씨, 이승빈 씨, 이정태 씨, 이충아 씨, 정상아 씨, 홍주표 씨, 김민선 씨, 김유신 씨, 배민열 씨, 배서령 씨, 배서령 반대주고, 서하연 씨, 그리고 조대현 씨, 최승규 씨, 김성주 씨, 미스터 마니케르, 오케이. 그러면 배선영 씨, Okay, welcome to lecture 17. Yes. So let's get started. Lecture 17. So I want to have a time to listen your questions. So once after our previous lecture, lecture 16, we had an online office hour, and 2 students joined that session. So asked some important questions. So I will share the result of that office hour, and you are welcome to join in the next session. Okay. If there is any request from you, so I will make another session. And I wanted to take another live question from you from now on. So if you have any questions, then please let me know. No question right now. Then I will just share the questions raised by students joined the online office hour. So in the previous lecture, I just drew the schematic diagram of our MOSFET structure. At the time, I just said that okay, there is a certain part called source and drain. So how can we fabricate this source and drain? That was not covered in our previous lecture, so I skipped that part. So I will just explain how can we actually fabricate the structure called source and drain. Everybody now understand, in order to make a certain terminal, certain contact, we have to introduce certain highly doped region inside our silicon and connect that highly doped region through a metal line. So since this is a source and drain, it means that this source and drain should be regarded as a highly doped region. Okay, then the role of our source and drain region is just the starting point of our electron's journey and the end point of our electron's journey. So it means that they should act as reservoir of our electrons. So if I ask you which type is required for this source and drain, N type or P type, then in our device called N MOSFET, so of course electrons are mobile carriers, so we need a lot of electrons in source and in our drain. So typically we use N-type doping and N-type doping for our source and drain region. So please note that the structure itself is built on our p-type substrate. So now we will introduce a highly doped n-type resins into this p-type substrate. Then there will be certain junction. So as you know, here we have a junction and we have junction. But you know that in this structure, so p-type, that is act as an anode of a p-n junction, and n-type, that is acting as a cathode of this p-n junction. Please think about the bias conditions applied to this structure. Usually, for example, this is source and substrate are tied. So it means that if we consider this left junction, we can find that this p-n junction is always at the equilibrium case. So no current conduction through this p-n junction. And please think about this junction. So here we have another junction, so between our drain and substrate. In this case, usually drain bias, the bias applied to our drain, is a positive or 0. So this is a non-negative value. So always drain is highly biased than the substrate, the p-type resin. So what will happen? In this case, our structure is, our p-n junction is located at in its reverse bias condition. So p-type resin is less biased than n-type resin. So in this reverse bias condition, you expect that really small amount of current flowing through this p-n junction. What was it? That was the reverse saturation current for p-n junction. So you know that in both cases, for both junctions, source substrate junction or drain substrate junction, they are either in equilibrium or in reverse bias condition. So we expect that very small amount of current is allowed through this substrate contact. Then remaining part, the remaining current conduction will of course will occur through this path between source and drain, and this source and drain path is controlled by what? Controlled by the gate. The gate is located on top of it, and by changing the voltage applied to the gate, we can control the conductivity between source and drain. That is the main part. But let's come back to other students' original question. So now, in order to make this source and drain, then we need n-type doping, and n-type means that here we need n plus doping, because we need a lot of electrons. So usually the doping density applied to this source and drain part is much higher than this p-type resin. So when I say much, means that at least 2 or 3 orders of magnitude higher than this p-type dopant. So p-type dopant, that is typically in the range of 10 to the 17 per cubic centimeter or 10 to the 18 per cubic centimeter. However, in the case of n plus regions, here we have source and drain, they are usually doped with typically 10 to the 20 per cubic centimeter. And they means that engineers are trying to increase the doping level as high as possible, so approaching to 10 to the 21. So that is usual target voltage for their engineering. So anyway, so this part is really highly doped. So for example, roughly speaking, 1,000 times highly doped than this p-type substrate. And you know that of course, this is just silicon. In order to connect this silicon part to the external world, of course, we need metal lines. Then where can you find the metal lines? Yes, now we can put a metal line, vertical metal line. Yes, this is fabricated just to on top of our source and drain region, and this is typically called as it has its own name. It's usually called as via. So you know this via means that something goes through certain structure. So this is called via, and here we have via metal, and that is directly connected to our source and drain. Now you understand what you do in the reality is just to connect our metal to ground and just connect to our rod metal to certain voltage source. Then that amount of voltage applied to this right contact is now acting as a bias voltage, drain bias voltage. So if you apply something, then you will have something. Okay, so I think that in the previous lecture I skipped the structural information about our MOSFET. So I just mentioned how can we actually fabricate this structure. So do you have any question? So I think that maybe you have additional question when I explain this facts, then it is really welcome. You are really welcome to ask additional question. Okay. So any question? So I will be very happy to have your question. And if you know, then let me just go to our main content, lecture 17. Okay. So previous lecture we have thought about the behavior of this structure. So our goal was now reduced to seemingly quite a simple one, like VGS minus VDS. That is our goal, to model the IV characteristics of this four-terminal structure called MOSFET. Of course, you know that in order to make it general as possible, then we have to introduce other expressions for source, gate, and body or substrate. But what we have assumed that gate current is identically zero because we have introduced perfect insulator for our gate contact, and yes, substrate in this case always PN junction between other terminals that is quite biased at the equilibrium or reverse bias condition, so that would be approximately zero. So the error is just the reverse saturation current. So now we can find that is also within very good approximation. So source current is just the same as drain current, and only the sign is changed. Of course, what is the sign? Usual sign for ID and IS, source current and drain current. Usually drain current is positive and source current is negative. So what does it mean? So I will explain here. When you draw the symbol of our MOSFET, then you know here we have no gate current. So gate current is 0, and here we have drain current. This is drain contact and this is a source contact. and here we have certain current conduction, and as we all know, actual current conduction just follows in this way. However, this is just to flow of our electric current, and we have to determine what is drain current and what is source current. So as I told you before, when we calculate or determine the value of terminal current, always the convention is the flux or the current flowing into the structure or the element through that terminal. Yes, here we have a terminal and the current component having this way. This is the internal structure of our element, and this is regarded as positive one. And if we have something like this, which is just escaping from our internal structure to external world, then that current is regarded as a negative value. So if we adopt this convention, then please think about what will happen to drain current and source current. Yes, certainly here from the viewpoint of drain, we have incoming current. So ID, drain current, is said to be a positive value. And here we have a source, and in the case of a source, exactly same amount of current is escaping from this MOSFET, so we will have a negative sign for it. Okay? So are you with me? Are you with me? Okay. Then anyway, I think that's all for our previous lecture, and now our goal is just to now derive the expression for our ID. So ID as a function of gate terminal voltage and drain terminal voltage. Of course, we are assuming that the source is working as a reference terminal. So source voltage is the reference voltage. So we have a relative difference between gate terminal and source terminal, or drain terminal and source terminal. Okay, so are you ready for listen my lecture? Okay, so now we have to think a little bit about internal structure of this MOSFET. So now we are going into a specific property of a MOSFET. Up to now, I have not thought about exact structure. So just saying that there is a 4 terminal, and the only argument that I have used was gate is perfectly isolated. That was used. So now we have it. But in order to calculate now the drain current, anyhow we have to think about the structure shown here. So the entire structure has a lot of components. For example, yes, here we have something and something and something and something. However, please, once again, when we had a PN junction, also PN junction has many components. However, after thinking about its electrical property, we realized that the only important part from the viewpoint of electrical conduction was the interface between N-type region and P-type region, the junction layer. So, if we follow the same argument, then we first of all find out which part is the most important part for our current conduction. So, if I ask, is this important? Is this important or equally important and important? So now you should be able to say no, because Br is a good metal, so it provides us really good conductance, and even this source and drain, they are highly doped. So in a relative sense, compared with this part, the region just beneath oxide layer, they are really highly conductive. So now we understand all of current conduction will be almost solely determined by this part. Now we will concentrate on this part. Of course, I should admit that, or I should warn that, considering only this part is an old story. So in nowadays, this and that, they plays a critical role. However, that is just state of the art, and as a beginner of this field, we will just concentrate on this part. Okay. So then, let me just think about this one. How can we consider the current? So current, think about this one. Let me just here. Yes, we will have a thin layer of electrons. Okay, we will have a thin layer of electrons, and think about a certain case like gate voltage is sufficiently higher than threshold voltage. Of course, even only when we have this condition, gate voltage is sufficiently larger than threshold voltage, we can have sufficiently good or sufficiently large amount of electrons in this part. Yes, so we have this case. Then, first of all, we will consider this condition. Drain bias is equal to source, so we have 0 voltage. Then you know that this structure is really symmetric. So between source and drain, and if we apply 0 voltage to this guy, and that guy, then the distribution of electrons will be also symmetric. So now you can see that if we apply 0 voltage to the drain, then we will have, yes, very uniform charge density there. Okay, so what I'm asking you is, please think about electron density at this part and that part and another part. Now I'm showing you 3 different, so can you see it clearly? So I'm showing you the point which is closest to the source and which is closest to the drain and the middle of the channel. So this region is called as a channel. So channel means that the channel connecting the source and drain. So this part will be called as a channel. And what is the difference of electron density or number of electrons? Here, here, here. Since we have applied 0 voltage, yes, this part is connected to, yes, 0 voltage region. And here we have applied also 0 voltage. Yes, this part is also directly connected to the 0. And since we have no voltage between this part and that part, you can immediately understand, even inside this position, any position, we will have just 0 voltage conditions. So do you have any objection? So now we have 0 and 0, and the potential varies anyhow in between this left value and right value. However, left value and right value are the same as 0. So everywhere in this channel, we will have just 0 potential case. So we will have a uniform channel. That is quite obvious, but I'm repeating this statement again and again because from now on, we will talk about another case where we apply non-zero drain bias voltage. Okay, so then please test your understanding. So instead of having 0 volt, typical case is you apply or voltage. Typical case is you apply voltage higher than 0. Then what will happen? So when you make a comparison between this point and that point, the difference becomes quite clear. Think about these two parts. So, and just to consider vertical structure. So when you consider this, the point close to the source part, then here we have gate, and here we have oxide, and this part, this point is directly connected to the zero bias voltage case. And then what will be the number of inversion charge? So the number of inversion charge will be just given by the difference between gate voltage minus threshold voltage, and of course we will apply Cox to calculate the current, and you know this is just charge. However, now I'm asking the number of electrons, so we have to introduce 1 over Q. Yes, so you can manage that one. But think about exactly the same case, but with, now please be careful, instead of this one, I'm now asking you what happens if I apply 0.1 volt to this source region. Then now, since this region is biased with 0.1 volt, you know this part is also connected to the voltage of 0.1 volt. Then now I'm asking you this question: what was the VGS? And now what is the VGS? Previously, since the source was biased to 0, so VGS, the difference between gate and source voltages, was VG. Good. But now, when you consider the voltage difference between gate and source, since the source is biased not to 0 volt but to 0.1 volt, now we expect that VG minus 0.1 volt will be the VGS value. It means that effectively, what happens? Increasing the voltage here, source voltage, just effectively working as what? Working as reducing the gate bias voltage. So now if we accept this concept, then now our inversion charge will not be no longer given by this amount. So we have same coefficient, but point is, now here we have to, originally we have to introduce the difference between gate and source, and now it is not directly related, only related to VG, but we have to say VG minus 0.1 volt minus VTH is required. Okay, so are you with me? Simply speaking, if we introduce a non-zero voltage to source, yes, effectively the difference becomes reduced. So we will have a smaller number of electrons collected in this inversion value. That is my suggestion or my explanation about this situation. Okay, but you know, source is almost always biased to 0, so don't worry about that. But if we go to the drain, then what will happen? Certainly drain is highly biased than 0. Then my question is now, effectively, from the viewpoint of our drain side, if we concentrate on this part, then what will be the inversion charge collected just beneath of this drain end of our gate? So you clearly understand this part. So there are tons of okay. So now you understand. If we draw in this way, let's say x, show x as a starting or coordinate for our channel direction, and let's say that this 0 is corresponding to your source end, and let's call large capital L as a drain end. Okay, then you know that we are now fixing the gate voltage. So at drain voltage equal to 0, then previously we had the inversion charge which is uniform along this channel direction everywhere, even this source end and even this drain end, they had the same amount of inversion charge. But now point is, if we, this is corresponding to VD equal to 0 volt, saying to the source voltage. But if we introduce a non-zero positive value of drain voltage, then now it becomes certain that although source end the electron density is the same, but at the drain end, what will happen? Can you expect? Where should we draw another dot for this point? So should we draw here or should we draw here? Certainly we have to draw somewhere here. Oh, so that becomes the starting point of our discussion and complication. If the channel is still uniform, regardless the value of our applied drain voltage, then everybody will happy. So let's assume that case. Although you just change your drain bias, then nothing happens to your electrons. Electrons are still there. Then what you can do is, I will show it right now. If electron density is not changed at all, then I will say like this: drain current is given by the number of electrons or charge of electrons, so minus Q times N inversion. That is constant everywhere, and just to multiply the velocity of our electrons. So are you with me? Then if we just collect the sign, so let me just think about the sign. Here, this guy, inversion charge, and inversion is number of electrons per unit area. Now you understand how do we have an inversion in this way, because oxide capacitance is given by farad per unit area. So and also when we apply or multiply voltage difference, so we will have the number per cubic centimeter. And since this minus Q is corresponding to what? Just to Coulomb, the charge, elementary charge delivered by an electron. So we will have the overall sign or overall unit dimension of this Coulomb per unit area. And how about velocity? Velocity, or its magnitude speed, is given by centimeter per second. So when we just consider the product between this minus Q inversion and velocity, then we will eventually have the thing like Coulomb per second and also centimeter in nominator part. So in the lower part we still have centimeter this is not good for our current calculation. Current should be, of course, ampere unit. You know that immediately you realize that this coulomb per second. What is it? Coulomb per second is the definition of ampere. So now you understand this is ampere, and it strongly means that you have some missing length scale in your derivation. So think about this one. Let's say that this is your MOSFET. This is your MOSFET taken from the top view, and this is, let's say, this is our source, and this is our drain. Now I'm asking you to calculate the current. So what you do is, okay, how many electrons are there? And you just take the area and counting the number of electrons and divide it by this area. Okay, now you understand the average density of electrons in your channel. Then now you calculate the velocity. Okay, each of them are moving quite fast. Good, but there is something missing dimension. Where can you find this missing dimension? The answer is amazingly simple. Think about this transistor. So from the top view, it's like a square. There will be certain current. Then please think about another transistor, just to looks like this. Much wider transistor. Same amount of voltage difference is applied. Then what will happen? If the current is the same, then everybody will make it the narrowest one goes without spending their area. However, it is certain that if we have wider and wider device, then what will happen? We will have more and more larger and larger current. So now it becomes clear the missing length unit in this part should be what? The width of your channel, which is hidden in this two-dimensional drawing. So when I just draw this way, it means that here we have source and here we have drain, and this is a channel, and I'm just showing just the cross section. Yes. However, there is a hidden dimension, this width direction. So that width direction is required. So I will say your ID is given by what? Multiplied the W of your channel. Okay. So are you with me? So then what will happen? In this case, if there is no dependence on the drain bias, so if our N inversion is not a function of drain bias, then what will happen? So let me just, of course, there is no such a thing. So as you know, N inversion charge density is a function of gate voltage and drain voltage simultaneously. But let's assume that inversion carrier is just a function of gate only. Then what will happen? In this case, we will have minus Q inversion charge density, which is a function of gate voltage only, and velocity here, and we will have W. Then what is the velocity? So velocity is simply given by what? Simply given by here. Now this is the position for velocity, or velocity is a vector quantity, so its amplitude. Speed is required, and this part we will just take the expression studied in our previous PN junction. What was the current, or what was the velocity of an electron when we have potential difference? So when we have potential difference, that velocity is given by so-called mobility multiplied by electric field. So this was the expression for speed of our electrons. So now mobility is given, okay, we have to introduce it. However, how can we model this electric field? Since the structure is really uniform along this way, so we will just uniformly distribute the electric field. Then what I wanted to say is, now this electric field part can be written as what? Written as V ds divided by our channel length L. So are you with me? I mean that this part here, this part we have 0 volt, and this part we have Vd, and 0 volt is Vs. So since electric field is uniformly distributed along the channel, then we have to say that electric field is given by Vd minus Vs divided by the length scale L. So Vd minus Vs is defined as, or denoted as, Vds in this case. So we will have this form. You know. Okay. So I would say yes, that will be our drain current when I'm saying that when inversion charge is solely a function of gate voltage. That will be the case. Of course, here we have very annoying sign here. Why do we have a negative sign? So we will think about this one. When we have this negative sign, the assumed direction of our current just positive x direction. However, please think about our convention. What was the convention for terminal current? Terminal current always should be incoming direction. So from the viewpoint of our source, this is the positive direction. And please think about from the viewpoint of a drain. Then what will be the right direction for positive drain current? Yes, this direction is the positive one. And what we have calculated up to now is just the one heading positive x direction. But in order to really calculate the drain current, we have to take into account the negative x direction. So without any ambiguity, we can just neglect this one. So please note that if we keep this negative sign, this is corresponding to positive current conduction, positive current component, but ID, drain current, should be directed to the negative x direction. So now we will have this form. So then let me just finish my unrealistic case with this final one. So now I'm asking you, how can you calculate Q times an inversion? So we have studied that expression. The collected charge just beneath the channel was simply given by what? C ox Vg minus Vth. Yes, this is just part 4, charge part, and we have velocity part, and finally we have normalization with our width. Okay, wide one will be more powerful, narrow one will be less powerful. That is quite obvious. If we have a wider device, then we will have larger part. So let me just collect them all and write it in this way. UN, I took it here, C ox took it. And yes, here we have W and L. So they are shown here, W over L. Then what is the remaining one? Then with this all of parameters related with material parameter. What is the material parameter? Yes, mu n. Mobility is the material parameter. If you have better material, then you will have better, means that higher mobility. If you have pure material or poor material, then you will have lower mobility. So this is material parameter. Then how about COX? Is this material parameter or device parameter? Can you change it or not? In this case, it can be changed by both of them. If you change your material, then permittivity of your oxide layer will be changed. For example, if you introduce hafnium oxide, then you will have a higher COX. And if you have just normal silicon dioxide, then you will have a lower COX. And here also COX is not only function of epsilon of that material, but also a function of oxide thickness. So once we keep the material composition, yes, think about just pure silicon dioxide. However, just reducing the oxide thickness, then you can increase the COX. Okay, so now you understand. And how about W and L? W and L is not, or W and L are not material parameters. This is solely given by just geometric consideration. You draw a rectangle defining your gate, and the size of the gate determines W and L. Okay, so as a designer, usually the freedom you can enjoy is W and L. So more or less mobility is fixed by the fabrication company. Of course, they are trying to maximize it, but they did their best. So as a designer, you cannot change mobility. And in the case of COX, yes, also the company has their best, so they can provide their maximum available value, but designer cannot change it. So designer cannot change the thickness of your oxide layer. The only thing can be freely changed by the designer is length and width. Okay, I want to very huge gate. Yes, you can do. Of course, you are now wasting your silicon, but anyway, you can do. Or you can try to make it minimize the shortest available length and shortest available width. Yes, it is only also your choice. So you can change it W and L with your choice. And after that, after all of this geometric consideration or material consideration, now we have a real electric part. The electric part is simply given by what? Vg minus Vth. I took it, and finally Vs. Now, after long discussion, we have arrived on expression for drain current. However, please note that this is not a correct expression. Why it is not correct? The reason was I assumed that inversion charge density and inversion is solely a function of gate voltage. Even when we apply, for example, high gate bias voltage, but we did not consider, yes, the reduction of charge density. So what you can expect is, in reality, your expression for what? For drain current will be modified by considering this effect. For example, think about this one. You have applied gate voltage to VDD. So, for example, 0.7 volt. And also you apply the same VDD to your drain. Then what is the difference between voltage difference between your gate and your drain? Obviously, 0. It means that this 0 voltage difference is not sufficient to make any of inversion charges. So if we have such a case, certainly we will have just negligible electron density here. So can you understand? So for example, let's say that if our drain bias voltage is happen to be quite close to Vg minus Vth, let's think about that. Then now our drain voltage is just turn on our MOS vertical structure, so the number of electrons will be quite small compared with the one highly turn on in this part was at the source end. So what you can expect is this expression is not perfect, and we will have a certain reduction term considering the reduction of electron charges with respect to the non-zero positive drain voltage. So we have to find out that one. Okay. So you know that in our usual lecture, in my previous lectures, I spent a lot of time about how can we rigorously derive this expression. But they are all recorded, and I think that this is not very interesting to students. So I love it. Actually that is one of my major research field. So I really like it. But you know, as a student attending this introductory course, so you are not very much motivated to derive it. So please watch it, the recorded video, so you will find it. So I will just tell you the result of this modification. So the modification is really simple, and it is given by half of Vd square. So please note that the dimension is important. So this term is given by what? The product between one voltage term and another voltage term. And now here we have correction factor, and it has also just a number multiplied by square of a certain voltage. So they are well matched in their dimensionality, and yes, this is corresponding to the correction. So so if you are interested, so please watch the recorded video, and you will find that how can you derive this one. In order to derive this one, you have to use this approximation. Your N inversion is no longer a function of gate voltage only, but you have to introduce this one, Cx and Vg minus Vth. If we stop here, nothing will change it, but we have to introduce another potential at a certain position. So at a certain position inside the channel, we will consider the potential applied, not applied actually, but build that certain position x. So what is Vx? V of x. So this guy has 0 for or this guy has Vs when the position is the source end, and if we have drain end, then this one becomes just Vd. In between, up to now we have no idea about what is V, the potential distribution along the channel, and just considering this expression, so this means that this expression we can derive the expression for I sub d, drain current. Okay, so do you have any questions? So for example, if all of you are asking me just to derive it, then I will try. or if you have another question related with this derivation or this description, then please let me know. But I think that it is most important for you to understand the concept. Why do we have this modification? It is because our channel is also reacting to the drain voltage. So if we apply higher drain voltage, of course, think about this one. If we apply higher drain bias voltage, then what will happen? Our electrons collected this channel region is more highly, strongly accelerated. So we will have larger current when we have higher drain bias voltage, because the number of electrons are the same and they are even moves faster, so we will have higher drain current. That is the first effect. However, if we increase VD further and further and further, eventually our channel will arrive at the situation, unfortunate situation, like there is no longer a channel at the drain end. In this case, it is not possible us to increase our current further. So now you can understand this behavior. But I have to say finally, as a final comment on this expression is required. Now we need a final comment on it. So where can we apply this expression? This expression looks really beautiful. However, this expression is valid at a certain limitation. So let me just write down. It is now assuming that this expression now assuming that your your gate voltage is larger than threshold voltage. That is understood. I mean that then what happens if your gate voltage is even smaller than VTH? Then you know from our assumption that then we can certainly say that drain current should be zero. Should be zero means that not exactly zero, but close to zero. Okay, so we are now assuming that the gate current, gate voltage is larger than threshold voltage. And think about this one. How about VD condition? Is there any condition for our VD? Then if you, okay, so that will be our homework problem. So here we have ID and VD. Let's just fix certain gate voltage that is fixed. Certain gate voltage. You know, gate voltage is much higher than threshold voltage, so we have still channel. Then if you draw, just to draw this ID expression, then how does it look like? So now you understand this ID expression is now second order polynomial of VDS. So here you have VDS, it's a square term and it's a linear term. Then how does it mean? So it means that when you draw it, so actually you will draw in this way. There is certain point and you will have a certain parabolic behavior. Of course, this curve always cross this 0 point. So think about this one. When you apply 0, what happens? 0 and 0. There is no constant term in this bracket. So when you apply 0 drain bias, your drain current is guaranteed to vanish. So this is okay. And you will have certain peak point. Yes, there will be certain peak point, and this peak point occurs when when does it occur? This is the condition where your Vd is equal to what? Vg minus Vth. So how can you verify it? Just to take the derivative of your ID with respect to Vds, then you will have a certain condition to have the maximum value. So the point where your derivative vanishes, that is corresponding to the point where your drain current maximized, and when you apply this expression, then the peak value we can achieve from this structure will now become clear. Yes? So mu n C of W over L, they are all shared, and when we have Vds equal to Vg minus Vth, then we will have just half of it, and Vgs minus Vth, and it's square. That will be the maximum current achievable for a given gate bias voltage. I mean that threshold voltage, you do not select the threshold voltage. Threshold voltage is fixed by the fabrication company. However, as a designer, you can select your operation voltage. Then, when you operate your device with a high gate voltage, then you can expect, oh, I can use a lot of current. But if you try to operate your device with lower gate voltage, which is close to threshold voltage, then what will happen? Then the maximum current you can achieve is relatively small. So then maybe once at a first glance, then you may say this way, okay, in order to have a powerful device, I will just increase gate voltage further and further. Then I will have a super strong device. Then that's good for our performance. So please think about this one. Why we don't increase our operating voltage further and further? That will be your. Just think about this one. But anyway, this is the graph of this expression, and please criticize it. Obviously, this is wrong. You know, the IV characteristics of your device should not behave like this. If we have this reason in reality, what happens? You wanted to apply even higher voltage to get higher current, but beyond a certain range, unfortunately, your current is reducing. That cannot be understood. So, and that does not occur. In reality, please note that all of our discussion is limited to the case where we have a sufficient amount of inversion charge. But when we have this condition, Vd equal to Vg minus Vth, then at this drain end, we have almost no electron at all. If we go beyond this point, if we increase gate drain voltage beyond Vg minus Vth, then now we break our assumption. Oh, throughout this channel region, we have a sufficient amount of electron. But now, no, that is no longer possible to follow that assumption. So, the approximation used to derive this expression, this beautiful ID expression, should be understood only limited to this part. Only before reaching to Vg minus Vth. And beyond this level, then we have to introduce another one, and the answer is amazingly simple. So up to here we just follow our beautiful expression, and beyond that, yes, this is just saturated. So this is called as saturation current. So now you understand, although this this is quite beautiful, but this is applicable certain voltage range. So could you please repeat? So I wanted to remind you the condition for applying this expression. Gate voltage, first of all, should be larger than threshold voltage. Otherwise, you don't have any channel. So no way. And also, in the case of drain voltage, your drain voltage should not too high. Otherwise, the derivation, the assumption used in your derivation is now breakdown. So your drain voltage should be lower than what? Lower than your gate voltage minus threshold voltage. Please note this expression. And if we have a different case, like VD is larger than VG minus VTH. In this case, in this second case, we will have just saturation current, and its value is simply given by here. This is the expression for your saturation current. Okay, so the overall behavior for fixed gate voltage and just changing drain bias, you will have this graphs. Any question? So I think that I have changed my style in this year. So previously, when we have this part, usually what I do is try to show you the rigorous derivation about this expression. But now, instead of showing the every detail of derivation procedure, I just wanted to give you the concept. The concept is, if we have just a uniform channel, we will have this first term corresponding to only linearly increase with VDS. However, due to the effect of charge reduction in this drain side, we have a reduction of current, and that is the main reason why we have a saturation. So saturation. Okay, so now we have just 7 minutes, but I have prepared 6 figures to be discussed. So let's cross fingers. Okay. So this guy. Please have a look at this one. So I think that I'm now delivering very important lesson to you. So even my students in the graduate lab sometimes do not understand this point. When you characterize your MOSFET, please, the most important one is this curve. So don't be pulled by other figures. First of all, when you ask yourself, how can I characterize the MOSFET, such a device, the most important one is this curve. Yes. So what is this curve? This curve is obtained by setting your drain bias to very small value. Here I have used just 50 millivolts, but 0.1 or 0.01 or 1 millivolt or whatever. So please apply very small amount of voltage to drain. Then why do we apply small amount of voltage to drain? We don't want to destroy the homogeneity of our channel. Now, when you apply this small amount of voltage, channel is almost uniform. Then the charge, just to show you how many charges are collected in your device. So this is the first condition. And just sweep the gate voltage. Then this curve is corresponding ID curve as a function of VG. So is it expected one or not? So if you understand our discussion up to now, maybe you will find that Okay, maybe there is somewhere here the threshold voltage, and below threshold voltage we have almost no current, and beyond the threshold voltage, and we have current increasing. Good, but you can find also severe distribution deviation from just linear expression. What we expect is just pops like this. But why do we have this reduced current? So you know, this means that our MOSFET does not collect enough electrons. No. Since when your gate bias voltage is beyond the threshold voltage, now this system really works as a capacitor. So your charge is really linearly increasing. However, still you can observe severe reduction. What is the physical meaning of origin of this reduction? Please note that current is determined by not only charge but also velocity. In order to calculate the velocity, you have to consider mobility. And we have assumed that mobility is a given constant. That is just a number. Yes, that is just a number, but unfortunately that can be a function of gate bias and drain bias. So usually if we have a higher and higher gate voltage, unfortunately mobility is reduced. So if we have constant mobility, then we will have this beautiful behavior, straight line, but unfortunately we have reduced current. So if I ask you why we have smaller current than expected current, then this is the reduction of reduced mobility is the physical origin of this undesirable behavior. Okay, so therefore, think about this guy. If we take the derivative of this curve, then where will be the point for maximum derivative? Can you find? So if you have this smooth curve, and please pick up. So pick a point. So in your mind, is this the point for largest derivative, or is it this? No. So certainly, so in my view, maybe this is the point where we have a maximum derivative. Okay? So as we will see later, we love this point. The point where we can find maximum derivative of this ID versus VG curve. So when you talking about the analog application, you really love to have this point. So why do we love it? So we will study later. So, but since time is up, I think that I have to wrap up 1 minute later. But please note that later means that next Monday we will discuss about different curves. So different, how can you characterize the MOSFET? But please note that although all of additional information can enhance your understanding, but the basic of this transistor, this MOSFET it is just a switch. So when you characterize it, first of all, you have to find out whether this is really turned on and turned off. So now you can clearly understand this is certainly turned off, and now this is turned on. And where do we have this switching behavior? Yes, around 0.2 or 0.25 volt, we have the switching behavior. So in my opinion, the most important first step to characterize the MOSFET is first to find out the threshold voltage. Sometimes even graduate students forget about that. So I ask them, what is the threshold voltage of this transistor? Although they have calculated every characterization about that, but they don't answer that the simple and fundamental question. So most important thing is, the first thing you have to check is threshold voltage. What is the threshold voltage of your device? That determines the property as a switch. Okay, so since time is up, I'm quite unhappy to have unexplained one. So we'll just keep this discussion till next Monday. Have your holiday.